Dear students, welcome back to Chemical Technology. So last modules we have seen the sulfur and sulfuric acid industry, then we have seen the nitrogen industry. So in the part of the inorganic industry, we will discuss about the phosphorus industry. So it's also the major part in the fertilizer industry. So we have seen already the phosphates. So phosphates which will include the phosphorus in that. So we'll just see the introduction to the phosphorus industry. So phosphorus in the elemental form and its many products is derived from the commercial deposit of phosphate rock in the mineral from fluorapatite, that is Ca10PA4 6 times F2. So this is the ore from which we obtain the phosphorus and other phosphorus chemicals. Then the major products of the phosphate industries are the phosphorus itself in the elemental form. So we have the red phosphorus and the yellow phosphorus in this one. Then we have this phosphoric acid, that is H3PO4. Then we have the ammonium phosphate that we have seen the earlier also. Then the calcium phosphate, the nitrophosphate, sodium phosphate and the organic phosphates. So we will discuss about each and the production method of this in the further slides. If we see the consumption pattern of the phosphorus, then the totally for the production of fertilizer in India. So the phosphorus industry that will mainly contribute to the fertilizer production in the India. Then the phosphorus content of a rock phosphate is expressed at the percentage of phosphorus pentoxide, that is P2O5. So wherever the raw material for the phosphorus production and the phosphorus other compound production, we will use P2O5 as a raw material. So the rock phosphate is always expressed as P2O5 percentage. So to start with, we should have some percentage of P2O5 initially. If not, or if it less than, then we have to go for the method which will increase the percentage of phosphorus pentoxide in the raw material. Then in the train as bone phosphate as lime, that is BPL, tricalcium phosphate content, that is Ca3PO4 twice is mentioned. Then high grade rock phosphate from Jamarcota, that is more than 30%. So it's a very good percentage of P2O5 in it for the superphosphate manufacture. I mean the phosphate content will be higher in this range. Then the rock phosphate from Jabua and Chattarpur for elemental phosphorus and in fertilizer mixers. So these two we can find in India where we can use the rock phosphate to produce the elemental phosphorus. And then lastly the Masuri rock phosphate for direct application. So this we can use direct application for the fertilizer. So these are the things, these are the grades of the phosphorus rock we can find in the India. Then clear beneficiation is required to upgrade phosphorus pentoxide content to about 30% for poor grade phosphate rocks in India. So suppose the percentage of phosphorus pentoxide is less than 30%. So what we will do? We will use the method that will make the percentage more than 30%. And we have seen the beneficiation method earlier also to increase the percentage of phosphorus in it. So beneficiation is required to upgrade the phosphorus pentoxide or to have the higher percentage of phosphorus pentoxide in the initial raw material. So commercial beneficiation plants in India, these are the RSMML in Udaipur, then Jamarkota, then Jabua and then Lalitpur. So in this state, in these cities we can find the P2O5 upgradation is taking place in their plants. And the rock phosphate imported from the Jordan, Morocco, Senegal, Florida and Togo to meet the market demand. So if the fertilizer industry is growing industry in India, also the plants or the crop yield we want more. So we have to meet the phosphorus fertilizer demand in India. So we have to import the raw material and then we can produce them into the fertilizer or we can convert them into the fertilizers. Then major reserves are in North America and in Africa. So these are the countries where we can find the most of the phosphorus content in rich form. So in the phosphorus industry, first thing we will discuss is the phosphorus or the elemental phosphorus. You can see it is obtained in the yellow phosphorus and the red phosphorus. Also we can find the other types of phosphorus in very trace forms like the brown phosphorus and the dark colored phosphorus. but mainly we will discuss about the yellow phosphorus and the red phosphorus. So if we see the properties of the phosphorus, then yellow phosphorus, so molecular weight is 123.9, it has a boiling point of 44.1 degrees Celsius, then boiling point is 280 degrees Celsius. The density is as 1.82 grams per centimeter cube, and liquid 1.74 at 45 degrees Celsius. It ignites spontaneously in air and must be stored under water. So these things we have to take care while handling the phosphorus, that it ignites spontaneously in the air. So it is highly dangerous to expose to air, so always you have to keep under the water. Then possesses disagreeable odor with extreme toxicity. So we always have to take care, and this is the problem becomes when we handle the elemental phosphorus to carry out the reactions. If you see the red phosphorus, the molecular weight will remain the same, but the melting point goes up to 593 degrees Celsius for the red phosphorus, whereas the density will go to 2.36 grams per cc. Then it exists in at least 6 different modifications. So we will see later on what they are. Then it is formed by heating yellow phosphorus to give higher degree of oxidation resistance and stability. So if we get the yellow phosphorus by the reaction, or the manufacturing will produce yellow phosphorus, then by heating slowly we can produce the red phosphorus, and that is mainly done to have the more oxidation resistance and the stability. If we see the consumption pattern for the phosphorus, then 18 to 20% rock phosphate to produce elemental phosphorus. So major thing of the major raw material as a rock phosphate, which goes to form the phosphorus, which can be further processed into different compounds. The major derivative is phosphoric acid, that is H3PO4, in the range of 50% aqueous grade to superphosphoric acid, that is 85% of P2O5, that is equal to 100% of H3PO4 plus 11% free P2O5. So it's like the oleum where it was the mixture of sulfuric acid and sulfur trioxide. So here if you see the superphosphoric acid, that means it will contain the phosphoric acid and it will have the phosphorus pentoxide in the free state. Then major use of phosphoric acid in food and detergent industry. The end uses of elemental phosphorus are the production of phosphoric acid, then phosphorus oxychloride, that is POCl3, then the production of phosphorus trichloride, that is PCl3, then phosphorus pentoxide, and the red phosphorus for matches and other use. So matchstick, if you have seen, then you can see it is mainly, the red phosphorus is the main element to form the matchstick. So if we see the method of manufacturing of the elemental phosphorus, so reaction will follow. So this is the rock phosphate, Ca3PO4 twice, and we use the carbon and the silicon. So the rock phosphate reaction with the carbon and the silicon dioxide, which gives the yellow grade phosphorus, and the calcium silicate is the byproduct, and also we get the carbon monoxide, which can be used for the production of synthesis gas. Then the yellow phosphorus, by the slow heating we can produce the red phosphorus. So these are the main reactions. So we have to use the coke and we have to use the sand in order to produce the yellow grade phosphorus, and also that yellow grade phosphorus we can convert into the red grade phosphorus. So here raw materials are low grade crushed phosphate rock. So this is the phosphate rock, then coke as a reductant. So the carbon over here in the coke form, it will reduce the phosphorus and it will get the reduced yellow grade phosphorus, and the sand as a flux. So the phosphate rock, the coke and the sand as a flux. If we see the quantitative requirement for this, then suppose if we are producing 1 ton of yellow phosphorus, then 93% if we get, then the phosphate rock, that is Ca3PO4 twice, will require the 7.5 tons. It may be 32% of P2O5 or 9.6 tons of 25% of P2O5. Then the sand for reflux we want 3.3 to 3.8 tons, and the coke you will utilize up to 1.6 to 1.8 tons for the 1 ton of yellow phosphorus production. Then the carbon electron consumption 80 to 25 kg, and this is mainly required to carry out the reaction temperature. So we use the carbon electrodes which will produce the heat that will ignite the reactor and the reaction will take place. So around 80 to 25 kg consumption will take place. And the electricity major amount required. So if we see here figure that 12,000 to 50,000 kilowatt hour is required for the production of 1 ton of yellow phosphorus. And the cooling water we require 200 to 250 tons. Then the plant capacity if we see, then 25 to 70 tons a day of furnace, and generally a plant will have 3 to 5 furnace to produce the elemental phosphorus. So here if you see the process flow diagram, then what we require is the phosphate rock, then coke and the sand. So if you see here the phosphate rock, then the grinder, it will grind the phosphate rock and it will create the very fine particles. So for the electrical resistivity, we want very fine particle size. If not, then we can feed it again and we can get the very fine particles of the rock phosphate. Then air require, the air is there, then centener, then we have to screen them to get the desired particle size. Then we are adding sand and the coke breeze. So here also coke breeze means very fine particles of the coke. So initially phosphate are grinded and then they are screened to get the desired particle size, then sand and the breeze is added. Then here the electric furnace is used. So here you can see the carbon electrodes. So we maintain the voltage 250 to 300 volts in 3-phase AC power. So it will generate the electricity. So the reaction temperature will go to 1400 to 1500 degrees centigrade. So here the reaction will take place and the phosphorus from the rock phosphate will be reduced and we get the elemental phosphorus. So here the one stream goes as the elemental phosphorus, then we have seen the carbon monoxide as a byproduct is forming and then dust. Then we are passing through the electrostatic precipitator to separate the any fine dust over here. Then the fines will go to the waste and the elemental phosphorus will go further. So here the yellow phosphorus we can store or we can send to red phosphorus conversion. So here whatever the sulfur we are getting, we can store as a yellow phosphorus. So from here the CO we will send to fuel or the synthesis gas, then we will cool down and we get the yellow phosphorus that we can store. Or we can send them for the red phosphorus conversion. So for the red phosphorus conversion, we are keeping in a batch converter. The reaction temperature is 250 degrees centigrade. We can have the reflex condenser over here. Then we are adding the Na2CO3 into it and the 1% of magnesium oxide to get it stabilized. So Na2CO3 is required and the 1% Mg required to get it stabilized. Then we can dry it and we can send the red phosphorus for the storage. Or whatever the phosphorus, we can combust and we can have the phosphorus pentoxide. So phosphorus pentoxide we can dry over the silica gel and then we can have the phosphoric anhydride, that is P2O5. Or we can have the final product as a phosphoric acid with the help of the phosphorus. So it is combusted, we get the P2O5 and then we are clearing out the dust particle in electrostatic demister. Then we are sending CO out and whatever the phosphorus pentoxide and they reacted, it will give the phosphoric acid. So that phosphoric acid we are storing in the purified 85% phosphoric acid, and then sludge which will have the CaSO4 or the arsenic and the silicates. Here also Na2CO3 required to remove the arsenic, which is the impurity in the final product, and also here we can add the lime to remove the impurities such as the arsenic. Then whatever the slag which is produced over here, it is also the economic importance. So that we are air cooled and then we are grinding. So crushed slag for the road beads or this soil liming or the glass manufacturing. So in short, if you see the rock phosphate which is grind, then we have the reactor with very high temperature and the temperature is maintained with the use of the 250 to 30 volt 3-phase AC power. So phosphorus, either we can store as a yellow phosphorus or we can have the red phosphorus conversion at the later stage. or we can have the phosphorus pentoxide, which we can dry and we can store as phosphoric anhydride, or we can have the phosphorus pentoxide converted to phosphoric acid and we can store as 85% phosphoric acid. The slag which we can use for the road beds or the soil liming and the glass manufacturing. So major engineering problems in the elemental phosphorus production are the electric furnace design, then second was the control and operation of furnace, and this third one is the safety and handling of the phosphorus. So what we have in the electric furnace design, we should have the correct voltage so that it will lead to the correct reaction temperature. So we want the reaction temperature should go or should be at around 1400 to 1500 degrees Celsius. Then only the phosphorus will be, or the phosphorus from the its compound form will be reduced and we get the elemental phosphorus. Also the second one is control and operation of the furnace. So here the feed will be changing, the feed composition of the rock phosphate will be changing. So we need to control and operate the furnace in such a way that it can take any amount of the raw material with the varying percentage of phosphorus pentoxide and we can convert them into the good grade of the phosphorus. And here in electric furnace design, if we need the phosphorus pentoxide as the final product, then we can feed the air into it, or if we need the only elemental phosphorus, then we can exclude the inclusion of the air in it. Then the last is the safety and handling of phosphorus. As we seen earlier, when it come in contact with the oxygen, it burns spontaneously. So always we have to keep in underwater. So when the elemental phosphorus if we require for the production of the different element, the different compounds, then we have to handle it very, very carefully. Otherwise, if you don't require elemental phosphorus, so it's better to convert the elemental phosphorus in its compound like phosphorus pentoxide, and then we can use for the other compound manufacturers. The next term is the economics. So in economics, we have to consider these things like the plant location, then selection of raw materials and byproduct uses, then the capital investment and the competition. So in plant location, so in the phosphorus production, the plant location becomes the not an important thing because the lots of money is always consumed in the electric furnace design. So here the plant location and other things become negligible in this case. Then the selection of raw material and the byproduct uses. So in this one, we want the raw material which should be at a higher percentage of P2O5. Also the byproduct which are using, that should be consumed to form the other compounds. So the process will become the more economical. Then capital investment, we have to invest more things on the electric furnace design. So this, it consumes more the capital of the total process. And the competition. So we have to see either we can have the elemental phosphorus and to produce other compounds, or we can have the phosphorus pentoxide itself without converting into the elemental phosphorus, and we can produce the other compounds using the phosphorus pentoxide. So the phosphoric acid manufacturing by the elemental phosphorus is become uneconomical, whereas the phosphoric acid production with the help of phosphorus pentoxide becomes more economical in this case. So these things you have to consider while considering the economics of the elemental phosphorus production. The next thing we will discuss in the phosphorus industry is the phosphoric acid manufacturing. So if you see the molecular weight, it's 98 and the forms H3PO4 twice and the water. So you can find in the hydrated form. Then melting point is 42.4 degrees Celsius. Then boiling point loses water of hydration from the hydrated form at 213 degrees Celsius. The density of 1.83 gram per cc at 20 degrees Celsius. Then it is completely miscible with water. Then we have the grades like shift in the concentration from 50% of phosphoric acid in water to an equivalent 118% solid, that is 100% phosphoric acid plus 11% phosphorus pentoxide. Then the shipping containers are made up of rubber lined steel or the glass to avoid the corrosion. If we see the consumption pattern, so phosphoric acid is largely converted into the calcium and the aluminum phosphates. So earlier we have seen in the fertilizer industry that phosphates are the more important in terms of the fertilizer. So it is largely consumed into the calcium phosphate or the aluminum phosphate. And the end users of this is fertilizer. So end users, if you see, it is used in fertilizers like the calcium or aluminum phosphate, or we can use in soap and detergents, then the food chemicals. If you see the method of production, there are various methods of production of the phosphoric acid. We have the wet process where 2/3 of production takes place. So this is the major process of the manufacturing of the phosphoric acid. So wet process is generally by the strong sulfuric acid leaching or by hydrochloric acid leaching. So we can have the production by sulfuric acid or we can have production by the hydrochloric acid. Then there is other method by electric furnace processes. So here we can have the direct conversion at plant site and the oxidation and hydration of phosphorus near consumers market, and we can have the blast furnace, but it is no longer used nowadays. So we will discuss about the wet processes and the electric furnace process, and in this we will discuss about the direct conversion at plant site and the oxidation and hydration of the phosphorus near consumers market. So if we see the wet process, and in that the leaching by strong sulfuric acid, then the chemical reaction will be the rock phosphate, then the sulfuric acid will give the phosphoric acid and the gypsum. So in this one, the gypsum we can send to the cement industry. So problem here is the filtration. So we will discuss how this problem occurs in the total overall the reaction. Then the side reactions are the calcium fluoride, sulfuric acid and the water will give the hydrochloric acid. And the hydrochloric acid with the use of sand we can convert into the hydrosilicates. So here this side reaction we are removing the hydrofluoric acid which are forming in the reaction zone with the help of the sand. So this is the main reaction which produces the phosphoric acid which is of our interest, and we can filter the gypsum off and we can get the phosphoric acid in a pure form. So the raw material required are the high grade of imported ore free from the impurities, that is rock phosphate. And if you see the quantitative requirement, so if we are producing 1 ton of 100% phosphoric acid in 90% yield and 2.7 tons of the gypsum, then the phosphate rock we require 32% phosphorus pentoxide, that is 2.5 tons, and the sulfuric acid which is 93 to 98% require 2 tons. And the plant capacities may vary from 100 to 150 tons a day of 100% sulfuric acid. Now if we see the production of this phosphoric acid in this, so we want the phosphate rock as a raw material. So the phosphate rock we are taking and then we are digesting mixture with the sulfuric acid in a reactor. Then whatever the sulfuric acid we are forming, so 2 things will be formed here. One is the gypsum, another is the phosphoric acid. So that we are feeding to the traveling filter where it will be washed, and the unreactor material can be sent back to the reactor. So if you see here, the filter will filter and the filtrate again goes back to the reactor again. Then here we get the washed gypsum, and gypsum we can send to the plant or the cement industry. And whatever the phosphoric acid we are getting, we can make it stronger. So here it will come. So we can have either 40% of phosphoric acid, or we can use the single effect evaporator where the water will be evaporated and making this phosphoric acid strong. So with the help of the single effect evaporator, we can have the 75% of phosphoric acid, and that we can store. Or we can feed this phosphoric acid and we can mix with 93 to 98% of sulfuric acid. Then we are neutralizing with the help of ammonia and we get the fertilizer over here. So we have seen earlier NPK that we require nitrogen, phosphorus and the potassium. So here we are neutralizing with the help of ammonia, and then we are adding the potash crystal to have the potassium content in this one. So the lower grade phosphoric acid or the phosphoric acid water we have stored, we will neutralize in neutralizing section in multiple reactor or neutralizing tanks, and we are getting the final grade fertilizer. We can have the potash crystal to have the KCl content in it, then the rotary granulator to make the granules, then it is dried in the rotary dryer. So air we are passing at around 150 degrees Celsius, then it will be dried and it will be screened, and then we can have this to the fertilizer. So chemical grade fertilizer to bagging and shipping. So this can be screened, whatever the oversized or the undersized particles that are again sent back to the rotary granulator. So here whatever the unreacted we can send to the nitrogen section again, and then again we can have the rotary granulator where it granulates and then dried, and then we can get the final fertilizer grade. And whatever the waste gases are there, we are scrubbing in this section. So if you see whatever the waste gases, they are recycled over here. So phosphate rack and the sulfuric acid will give you the gypsum and the phosphoric acid. Then we are washing it. Whatever the weak acid wash, we are recycling back. Then gypsum we are washing, and then we are sending to the cement plant. Then we are getting the phosphoric acid. Either we can directly use for the fertilizer manufacture, or we can have the concentrated phosphoric acid. So concentration can be increased by the single effect evaporator. Nitrogen section we are adding sulfuric acid, ammonia, and then KCl, which we can granulate, then dried and then screen to have the final grade fertilizer. Then in this one, the major engineering problems are the process design, where the fineness of the grind, the temperature and the control of the sulfuric acid. So here the major power required to grind the phosphate rock. So here if you see the reactor time in hours and the percentage of rock reacted. So if you see the time required for the 200 mesh is less when compared to 100 to 150. So means if more is the fine particle size, the reactor time will be less, and we get the higher conversion of the rock phosphate. So means we have to grind it very finely, but while grinding it, it will consume the more power, and we have to bear the cost for this one. So here if you see the grinding cost, so very less the particle size, the grinding cost will be very high, but at the same time the reactor cost will be reduced. And if you take the total cost, so here we can have the optimum point. So around 200 mesh we can grind it, so that reactant time will be less. Means if time is less, we can produce the product more, and we have the more conversion of the rock phosphate into the phosphoric acid. Then the metal of construction if you consider, so the reactor is steel lined with the acid proof brick, and the all air vents, they are the PVC coated, that is polyvinyl coated steel. Then the storage tank is rubber lined steel. Then the filter type 316 steel with polypropylene filter cloth and the rubber lined vacuum receivers of the steel. So this lining or the coating we require to avoid the corrosion due to the phosphoric acid. Then after the sulfuric acid, we will see the hydrochloric acid leaching method. So the reaction are almost same. Earlier we are using the sulfuric acid. Now we will use the hydrochloric acid. So the phosphate rock with the reaction with hydrochloric acid will produce the phosphoric acid and giving the calcium chloride as the byproduct. In this one side reaction, again the hydrochloric acid will be formed, and we can take care of this hydrochloric acid with the use of the sand. So here the raw material are the same. So phosphor pentoxide content should be more than 30%, and the HCl, the grade we want more than 30% strong. In organic solvent, it may have the C4 or C5 to extract the phosphoric acid from the calcium chloride solution. Then the quantity requirements are, if we are producing 1 ton of 100% phosphoric acid in 98% yield, then we require the phosphate rock as raw material, which is 32% in phosphor pentoxide. So we require 2.3 tons of it. Then the HCl 100% we require 1.4 tons. In the solvent makeup, that is butanol or amyl alcohol in C4 or C5, 3 kg. Then flocculating agent 0.4 kg, and the generally plant capacities will vary from 15 to 150 tons a day.